Alright, so let us start today. Since we didn't have a class on Monday, so let us quickly try to finish off the remaining portions on this. So if you remember, if you recollect on where we stand at this point, so we had started discussing on DES. Actually, they are all leading towards DES, and we were discussing on certain tools which will be really helpful at some point while discussing the data encryption system. And in that, we started with the two important elements. One was Pbox, the other one was Sbox. And in case of Pbox, there was three types of Pbox. Primarily, it was indicating that it will be a relationship or a mapping between the input and output. That was the primary concern with it. Now, how it can be made, those mapping between input and output, was the point of our discussion. And in that, we have found out that there can be three ways of doing it, as at least in terms of Pbox. One was the straight Pbox, the other one was compression, and the next one was the expansion. And mostly, as I said, you will find the expansion box will be used some point later as well. But we are at this point, since we are discussing a generic approach towards the different tools, so the straight box and the compression box can also be considered for our discussion. And in that way, you can see, like from the diagram, it was very clear that how the input and output are to be mapped accordingly. And based on that, we went on discussing something in terms of when the inputs are 64, and I told you that this is one of the standard table that we are going to follow in many places. You will find that for different set of algorithms, we will have a predefined table which will indicate again the input and output relationship. Just like in over here, this is an output table where the significance was that the 58, the first letter, first number in the first row is indicating that what should be the output. The first output will be the 58th input. So that's what the table is indicating. Similarly, you will observe the last one, which was 7. It will mean that the last output, the 64th output, will be nothing but the 7th input. So that was the significance of this table and how to read this table. Because again, please keep in mind that these tables will be forming the basis of our discussion for DES and the key formation. So it will be really confusing later on if you are not able to figure out this table right now. Okay, so please keep a track of this. Keeping this in mind, we went on discussing something in terms of Sbox, which was called as the substitution box. In that also, we found out that this is more like a generic approach towards the Pbox, because in this case, it can be the case where the input and output may or may not be equal. And it can be invertible, it may or may not be invertible also. So it is more like a generic approach to the Pbox. It can be used as an expansion box. It can be used as a generic compressing box also, or a straight connection for that matter. So keeping this in mind, we found out that there can be a linear Sbox. And in that, a linear relationship can be existing between the input and output. And in those cases, we find out that we can have a scenario like this, where x1, x2, x3 are the inputs and y1 and y2 are the two outputs. So 3 input and 2 output. This is the scenario we are in. And in that case, we can represent it in terms of some kind of a matrix in leading forward. So this is where we ended our discussion, and also we found out the different arrangement of Sbox, and in that we found out that this is one of the very common rule is imposed. Although in this case only 3 bits are considered. But you will find that in DES, we are going to use 64-bit, or rather, to be precise, we are going to use 56 for that matter. So in that case also, we have to follow certain rules in which mostly the 2 outermost bits will be considered as the rows, and the middle element will be considered as the different combinations. So for that, we found out this as a very important example for us. And as you can observe, the last 2 bits, the outer 2 bits has been considered as the row, element, and the middle bit portions are the different combination. And if you observe the middle portion over here, this element over here, this has been predefined already. So based on the combination that we have with respect to the 6 bit, which is coming as an input, we will get 4 different output based on certain table. Okay, so this is again basic important part is again, as I keep on telling you that this is an input and output relationship that is existing with respect to a table. Now the internal values over here, for example, this is 10000, or this is 0111. This is following certain rules for that matter. If it is a linear, we will have certain equations for it. Or if it is not, even the equation is given, you can have a predefined table, and based on that you can form the S box. Now this table is not a single table that will be existing. There can be multiple combinations on which this table can be formed, and based on that the different outputs will come. Right? So this is where we stand at this point. So keeping this in mind, let us try to solve few small little numericals so that we can understand where we stand for that matter. So this is a fun question that comes in mind. This is with respect to the combination of keys, the length of the key that we had considered. A transposition block, this is just to recap on what we have done so far, because it's I can feel that there might be a chance that you are not following it carefully and you might miss out some of the things. So this is the first thing that I thought of taking one of this numerical. A transposition block has 10 inputs and 10 outputs. Alright. What is the order of the permutation group and what is the key size? What will happen if substitution is used? Suppose this is the question given to us. This is a question given to us and we try to find out what are the combinations. Anyone amongst you who can tell me what were the relationships existing between the number of bits and the number of combination, the key length that we had discussed? If it is a transposition, what was the formula? Anyone? There was a formula in terms of log to the base 2. Log to the base 2 n factorial. So that was the following up. So here in the same manner you have 10 inputs and 10 outputs. So basically this is what is trying to be. I'm just rushing this part a little bit because this calculation part is relatively easy. If you have a calculator you can do it very quickly. But just see the way it is being done. So as you can see, since it's a transposition, the first part is with respect to a transposition, the order of the group will be nothing but n factorial. This is already being done in previous classes. It is just a recap of it. So it was n factorial. Since n is here 10, so we have 10 factorial. So the order of the group will be considered as that. So 10 factorial is given by that huge number. And now as it is a transposition, we have a scenario, the formula was log to the base 2. Just to remind again, this formula already we have done in the first few classes on modern block ciphers. So in that case, we are getting 22 bits. So the key size is 22 bits. And as far as the 22 bits, so the number of possible combinations that we can have is 2 to the power 22, because that was also given 2 to the power n factorial, it was there. So this was 2 to the power 22. So 41 lakhs 94,000 odd combinations are there. So the question is that out of those combinations, this many number of combinations can be used for the key. But this is with respect to transposition. But as we know that the transposition we are not very aware of and we are not going to discuss much on it. So let's see how about the substitution technique being used. Because remember in substitution the formula changes to a relatively bigger size because the log to the base 2 will have 2 to the power n factorial also. So this is the answer for the second part of it, where we are getting the order as 2 to the power 10. So please remember this one, this change. Here it is n factorial, here it is 2 to the power n factorial. All this has been done previously. It's just the repetition of the same thing with a numerical. Alright, so this is the 1024. And another change that you are observing, that the formula here will be log to the base 2 to the power n factorial, which makes the key size eventually around 8,770 bits long. It's a huge number, and that's why there will be so many big number of possibilities of different combination that is possible. And naturally you can imagine that the security purpose also substitution technique is much better, because the randomness on the key will be relatively much more compared to a transposition. This example is like all these equations have been done previously, just the application of the same. Right? So this is one of the examples. The second example that I thought of telling you is with respect to the relatively newer part of it. Suppose this is given to you, this graphs, or suppose the diagram is given to you, which is the same diagram in fact what we have discussed in the previous class. So show the permutation table for the straight box in the figure, and also for the compression and the expansion box. So what do you mean by permutation table? That's my question is over here. So what do you think as a permutation table will be there for the first one? That also we had actually discussed eventually, but this is in terms of a numerical I'm talking about. What will be the permutation table according to you for the first one? Straight box. What exactly is meant by permutation table? What will be meant by permutation table? Permutation table is nothing but the relationship how the input and output are related. Or rather, I can say the output table, the diagram that I showed you. How in the output table, the first output is related to which input? That's basically the permutation table. Remember this diagram, this table that I was showing you. This is basically a permutation table. So this is an output table, but basically what it indicates, the first output is related to 58th input. Right? So that's how the table has been formed for n equal to 64. Now in this particular question, what they're asking is that given that you have a diagram like this, what will be the permutation when it is a straight table? It's a straight permutation. So can anyone tell me that? So maybe we can say this will be the permutation table. Why? Because you can see the first output, read it this way, that this reading is very important. The first output is related to the second input. You can see the first output is related to the second input. Please offer this a little bit more attention. The permutation table is nothing but a relationship between input and output. But what exactly does it mean? It is basically the output table that we are looking at. Now, these are my outputs. 1, 2, 3, 4, 5. Now, go back and see that these outputs are connected to which particular input. So, the first output over here, first index of the output is connected to 2. So, that's why that is counting over here. Second output is connected to 5. 5. Understand, this is only for 5 plus input. This if you go on extending for 64, those 64 table is that 58 one that table I was showing. This is only for 5 bits, that is for 64 bits. So for 64 bits, there can be some kind of a combination that is present. Based on that big table is formed. Whereas this is 5 table, you are arranging it this way. So fourth one, so don't read it this fourth way. It's like third output is connected to fourth. Got it? So that's basically the permutation table for a 5 element or 5 input element. Now if that you have understood, can you give me the permutation table for the compression and the expansion box? For compression box, can anyone please tell me what will be the permutation table? Same thing. First output related to which input? Second output related to which input? Third, which one? Fourth, which one? 5, which one? This will be the table, permutation table. Why? Why this will be a table? Because if you observe the first output is directly connected to 1. So 1. Now if you observe second one over here is connected to 3. And fifth one is connected to the third output is connected to 5. So that's why this 3 exists. Because it's a compression box, because it's a compression Pbox, and as per the table, 2 and 4 has been considered as blocked output. Okay, so that's why no such connection exists. So that's why this will be the permutation box. In that same light, can you give me the expansion box then? Because there are repetitions possible. So 1, 3, 3, 1, 2, this will be the expansion box. So please make a note of the term permutation table and the way these tables are to be given or found for a given S box or a P box combination which is given to us. The reading of this table is so very important leading towards further. This is with respect to smaller number of bits, but when you consider for a longer range, for example 64 as that's a standard for DES, the table will be a big one. That table reference is given in the previous slides or the material uploaded. You will find that 58 and all whatever is there, and the last bit is 07. So that's for the 64 bit, that whole set of elements are formed. Yeah. So this is one of such question that comes in. Right. So this is about the one of such question. Second one. Now suppose this is the given question. The opposite way. Suppose a Pbox, show the Pbox defined by the following table 8, 1, 2, 3, 4, 5, 6, 7. That means you have to draw the Pbox. You have to draw the Pbox if you are given such a scenario. Like the permutation table is given, you have to make sure you draw the Pbox with the certain connections that is exist. Can you please do it and then verify it over here? I'll give you the solution after this. Just take 2 minutes and form the Pbox. Make the connections accordingly. Make the connections accordingly. So it will look something like this. It should look something like this. Okay. So similarly, here 8, 1, 2, 3, 4, 5, 6, 7. So this is how the thing stands. But remember, read it this way. The first output is connected to 8 input. Second output is connected to first input. Third output is connected to second input. Like that you read. Don't get confused with the numbers placed on the block. Read the index. First, second, third, fourth, like that, so on and so forth. So please read that. Accordingly you read it. So are you done? Are we done? Let's see if we are all at the same page. Alright, so this is almost the diagram that we are looking at. Hopefully you can all relate to it. You can see that the first output is nothing but connected to 8. So this line you have to draw. Similar question might come in where you are given a certain set of elements and you have to draw the diagram to see that whether it's correct or not. But as you can see that if anyone you are reading wrong, overall Pbox configuration will be wrong. So be very careful in reading the element. With single line it's okay, but with more number of elements it might be a problem. You have to just keep a track of the connection. That's it, nothing else. You can even form a table. What I did when I was practicing all these things, I form a table. Output index 1, 2, 3, 4 like that, and the connection how you are made. Because it's easier than the reading purpose itself. But if you are comfortable in overall looking at it and by inspection you can do it, it's no problem at all. You don't need to show the steps at all. Okay? This is another type of question. Same thing, but with respect to this 1, 1, 2, 3, 4, 4. This is again determine whether the Pbox with the following permutation table is a straight box or a compression box or an expansion box. Can you first tell me that? Why it is expansion box? Because there are repetitions of output. 1 is repeated twice, 4 is repeated twice. So basically there are more than one combination that is available. So that's why it's definitely an expansion box. Now the question is how they are connected, which I think by now you are in a position to draw or rather explain. So this will be the diagram for that matter. Right. So this type of questions, I guess all of you have understood that this kind of questions are very common, except that this table may be a little more longer. Okay. There might be more than 5 element or 6 element, and based on that you have to form the table. But it's very scoring. Don't miss out scoring from this point. Okay. It's easy. Just understand the concept and apply. Shall I move? All right. Now we have another question. This is another set with a different note with the concept of invertible option. So the question is the input-output relation in a 2x2 S box is shown by the following table. This is given to us. Show the table for the inverse S box. Let's see whether we are able to understand that. Inverse S box we have already discussed that whenever M and N are equal, that was the condition. When the input and the output are the equal, then whatever we have done in the input side, that is in the transmitter, In the reverse side also, we can form a table, meaning that given the output, given the received output, we can find out what was the input. So if you are given this particular job, that input left bit is 0, 1, because it's a 2 cross 2, so 2 input are given. So you can see 0, 0 has been marked over here. Similarly, 0, 1, 1, 0, 1, 1 have been marked over there. So all the possible combinations there. And these are the initial permutations available with us. Can you draw the output table with the concept that whatever you are getting over here at the transmitter, same thing you should be getting at the receiver. That means that if you are here, the input is 0, 0, your output is 0, 1. Remember the process what I mentioned, 0, 0, wherever it intersects, that will be your output. Your 0, 1 giving you output 1, 1. 1, 0 is giving you output 1, 0, and 1, 1 is giving you output 0, 0. This is what the initial trend is indicating. Now my question is how to do the opposite way in the reverse direction so that we get the following inputs at the receiver. Can you suggest the table? How will it look like? Similar to table, because the table is what is important. How will you arrange the zeros and ones and especially the shaded, the gray part that you are looking at the receiver end? How you are going to do it? Did you understood the question first? This is my transmitter. If transmitting 0, 0, we are getting 0, 1. If we are transmitting 1, 0, we are getting 1, 0. Suppose this is the initial pattern that we are going on following this. Now the question is at the reverse side, when we have 0, 0, or we are getting an output of 1, 0 rather, we will be getting a 1, 0 output. Because receiver side, this is my input, right? And this is my output. So my question is how the table needs to be formed in order to get back that output. Suppose this is my 0, 1, 0, 1. That is at max we can do. Now my point is what will be the in between element. So first of all, let's start with 0, 0. 0, 0. 0, 0 is coming where? So the internal element will be 1. Can you understand this? What I'm doing? Based on this input, 0, 0, we got the output 0, 1. Now the point over here is the reverse process in which these inputs are like this and the output should be of this nature. So the point is that what I'm making over here, 0, 0 is the input, 1, 1 is the output. So 1, 1 I have made. 0, 1. 0, 1, 0, 0. 1, 0, 1, 0. 1, 1, 0, 1. So this table will be the reverse table or the inverse table to that of the Pbox which is there in the transmitter. Got it? How this to be made? Now if it is a 3 cross 3, same applicable, only that the number of bits will be 3. That in fact we did it some time back while solving I think one of the question at the, this one. This we did last day's class itself. Same principle we are applying. So the input has become the output. Now the reverse process we have, the output is there with us, which acts as the input. So we have to now use the inverse box to get back the input once again. Right? So that's the example, that's the theory part, and the example is what we are getting over here. So that's the output that we have done. So let us now, so that's all type of kind of question that you can expect out of this part. So let us quickly move ahead with the other portions, other rules or the tools I was saying with respect to DES, continuing from that Pbox. So the next thing is that exclusive OR in block ciphers. This is the only operation that you should know. Already you know it, but basically this will be the operation that will be followed throughout. Whenever we have the plain text or the message element and you have the key, they will be XORed in some way or the other. Maybe the full element, full length of the key or a partial of the key, whatever it is, this will be the only operator that will be working. So that's why this is mentioned over here. And the interesting part is that this operator, when acted on any element, it will form the group also. It follows the group property. Alright, so this I'm skipping for the timing because group property and all those commutative associative rules and this we have already discussed. In that, one, like as I say that at the end, one I have mentioned that this is very important. X plus X, like any element from that set XORed with the same element will always be the identity element. And the identity element over here will be 0. Okay, so that is one very important thing that you should note down. So X plus XOR X and anything for that matter will always be 0. Same element if XOR, it will be coming as 0. That's the main bottom line. Because you will soon find that this particular principle will be used in some place, somewhere down the line. Alright. So I'm skipping this slide for the timing. You don't need anything because nothing will come over here. Another thing that is advantageous with respect to XOR is the invertibility property. That means that if you are getting the output which is XOR K, the X is the message and K is the key, and the opposite side X can be retrieved back quite easily with respect to K and Y. But they are having a XOR operation. So in both the way, it follows that property true. And that is also a very advantageous scenario because definitely we need to decipher back, we need to get it back the information. So that's why the operators are like that. But the point over here is, how do we get this K? That is where the significance lies because everyone knows that there will be an XOR. But how that key is formed is what makes it vulnerable to the cryptanalysis. The more secure we can make, the more random we can make it, the better is the security. Because the rest of the operation will be known to everyone for that matter. So let's move ahead. Now another property that comes with it, again this is a part of our DES leading towards the tool and that is called as a circular shift, which I think many of you might be already knowing it. But here what happens is that another component found in some modern block cipher is the circular shift operation. Now if you observe over here, shift left by 3 bits. So what does that mean? Basically you have the B0, B1, B2. So this element, these 3 elements, the blue colored one has been shifted towards this side. So after shifting it has come over here. Okay, because left shift means it is like this. It is coming this way. Okay, it has been shifted. And on the other hand, this is the right shift operation. So any bits you can have, how many number of bits you want to shift, because that also is a part of the creating a random element, randomness in the element. Because remember this B0 to B7, these are all ones and zeros. So based on ones and zeros, if you are preponing this or appending it at the bottom, like back or 4-bit or 3-bit you are appending, the overall configuration of 1010 pattern will be different every time. So the circular shift also will be playing a major role for the improvement of the randomness. That's one. Second one, what we know is called a swap. This you please make a note because there is a certain rule to it. So swap is, the operation is a special case of circular shift operation where the shifting will happen k equals to n by 2. That means that if n is equal to 64, so 64 by 2, suppose, for example, so 32 up to 32 bit, or let's take a relatively easier example, when you have 0 to 8, in this case 8-bit word, is easier for us. So 4-bit will be swapped. How will it be swapped? You can observe here B4 to B7 has been swapped this side. And B0 to B1 is placed over here. So this process is relatively important because in most of the cases, especially the Fiesta algorithm that we are going to discuss right now, you will find that this is also a part of, along with the circular shift, this particular operation will be used, where there will be a portion of the bits will be appended in this particular order. And you can see the decipher also, it will be reverse. This part goes in the left hand side, whereas the portion which we are left with will come in the right hand side. So that's one of the operations. You can see that this operation is valid only if n is an even number, which in most of the case is. Left shifting n by 2 bits is the same as right shifting of n by 2. This component is self-invertible. To prove that, let's take an example. Okay, we'll take that example. Let us split this part. This is all another thing, split and combine. So one is circular shift, we understood. One is swapping of the bits we have understood. The last one is split and combine. That is there where you can splitting up. You can see the imagine diagram here. So we are splitting it up and then we are combining together. So it's a 8-bit data. Now it has been made it to 4 and 4. Right? So that's how the thing works. Okay, so that's also easier for sometimes for the calculation. The internal processing happens to be much easier when you are considering this way. And this all will be used at some point. So these are the operations we call it. And you can see the cipher in the other way, we are actually combining it. Okay, so splitting is in the transmitter side, combining we are doing it in the opposite side. Okay. Now let's see that this is one of the simplest of example. One is given that show that the result of a 3-bit circular shift on the word 101111. Very simple, 3-bit, you have to just shift it. So I'm not taking much time over here. So those last 3-bit 100 over here has been shifted of this side. And now this has a new combination, as I said. Right, so that's already you have done, I think, long back. So same thing we are applying. And now let's see about the swapping of the word. So this is another word given 1001111. Now the question is swap the word resulting from part A. And then compare the result of part A and part B to show that swapping is self-reversible. And that is quite easy because here we have 8 bits. So 4 bits should be swapped. So if you observe from the diagram itself, it's very clear. So these are the 4 bits, this brown color one. This has been swapped to the right. Okay. And on the other hand, the same thing has been re-swapped. And in that way, we have found out the original message once again. So part B and part A is giving us the information that they are self-invertible. And whenever we are swapping, the decipher part or the decryption part will be just the opposite side. So we are getting back the data while we are moving in the opposite direction. Just a simple example to prove that. So this splitting, the circular shift and this swapping part particularly will be really useful after a certain period. So please keep in track of that. At that time, we are not going to repeat that much. We are going to directly apply. Now we come to the next one and the most interesting part of our DES. After we have learned all the tools, the two most important thing that constitutes DES, and that comes from one thing called as product cipher. Now, product cipher was ideally defined by the term by Shannon, and it was two important property which was considered. One, as you can observe, one is called as a diffusion, the other one is called confusion. Alright, so diffusion, the main objective is to make sure, the idea of diffusion is to hide the relationship between the ciphertext and the plain text. So please make a note of this, that diffusion always makes an effort to hide the relationship between the ciphertext and the plain text. Ciphertext is what after the encryption you have got. Plain text is basically the message. So there must be some relationship that exists between those two. So diffusion will be a process to make that not happen. So that even if you get the ciphertext, you are not in a position to get back the plain text easily. On the other hand, the confusion takes place when there is a ciphertext and the key is made hidden. When you hide the relationship between the ciphertext and the key, that how the key is generated or what is exactly the key, how it is changing the plain text to ciphertext. So all those processes should be done. That is why you will find that soon after a certain period, we are going to use Pbox as well as Sbox in our discussion. While Sbox will be used for the substitution part, Pbox will be used for the permutation part. So there will be one for the diffusion case and the one will be for the confusion mentions. Right? So let's see one by one. So this, and you can see that this is very important, this term for that matter. Diffusion and confusion can be achieved using iterated product cipher, where each iteration is, as I just now I said, is a combination of S boxes and P boxes, and this will be considered as rounds. So one round will have multiple S box, multiple P boxes. After that round, the output which that first round gives you, that will be fed as the input to the next round. The next round will also have the same number of S boxes, same number of P boxes. It will generate second element. That second element will be input to the third element, third round. Like that, round will go on. This round for DES will be 16 rounds. 16 rounds, and the data set is of 64 bits. And all those 64 bits will be taken care of with the property of this swapping, circular shift, split and combine. All these things will come in. So you will soon find that the complexity of calculation becomes really difficult with this point. But even in that, DE is not secure because the key length is of 56 only. Okay. So we'll see one by one how it, but the round is basically, this is what the round is. Already I told you about this, so I don't think we need to do much discussion on this. The idea of diffusion and idea of confusion. You can see the this will frustrate the adversary who uses the ciphertext statistics to find the plain text. That's the main purpose. Whereas the confusion is who tries to use the ciphertext to find the key, to make the cryptanalysis or the intruders not to get back the key easily. That's why these two methods have been used. So that's all. Now rounds, again I told you that rounds, what are these? N round ciphers. As I said, 16 round cipher you will come. And unfortunately, I think you will need to do some round of calculation for your CAT2 questions as well. Whenever the question comes in, the output after a certain round will be asked to you. And in that way, we'll find that the things will get really difficult at times. So anyway, I'll give you that. So you can see that the plain text is encrypted n times and the ciphertext is decrypted n times. Naturally, the number of rounds will be same one after the another. And the middle text is somewhere the intermediate value. So we'll see one by one what are these elements. This is one of the conventional block set. Okay, please, if you observe carefully, you can see the left hand side, the diagram that you have over here. And in that, it is only a 8-bit plain text. It's only an 8-bit plain text. Now, as I keep on telling you, 8-bit will be 64-bit later on. Now, 8-bit plain text, if you see the flow, workflow, how it is done, you have an 8-bit text is mixed with a whiten or a key. So this is called as key mixture. And this key is an element where K1 is fed. And where is the K1 is coming? K1 is coming something called as round key generator. So there will be an algorithm. You are sending the key. The round key generator will generate some random key like K1, K2 up to Kn. In this case, you can see there are only 2 rounds. Why? Because this is K1 and this is K2. Only 2 rounds we are discussing. So K1 and K2 will have 2 such keys which are random to each other. So K1 is fed over here and that makes the 8-bit plain text which has been already divided into 2-bit at a time. You can see over here. And now the middle text is formed. This whitener will make the data hide. The raw data plain text which is coming is now hidden. Now after that is hidden, from that mixture box, you are looking at S box. Now we see that we know S box. What exactly is S box? So in that S box, what is happening, that we are looking at the 4 bits. You can see here the output of S box. The value of the bits are changed based on the structure of the S box. What is the structure of the S box? That's basically where the permutation table comes in. How you have specified the S box? Remember the S box 2 cross 2, 0, 0, 0, 1. How you have made the table? So each of these S box will have a certain permutation table. Remember that this one, I'm talking about this 0, 1, 0, 1. Suppose 0, 0, 0, 1, 1, 0, 1, 1. Suppose this is my table. So each of these S box will have certain amount of table picks where 2 inputs are coming and 2 inputs and 2 outputs are generated. So these are the 2 outputs after the S box, which are the combination of the individual X boxes. Can you understand now? That's why I did the numerical before. Now after that is generated, there is a Pbox, and in this case it is a straight Pbox which is being used. Now all those bits which are coming there, 8 bits for that matter, is going through a combination of set where the Pbox has been made in this order. This is just an example. It can be anything. For example, here the first bit is connected to 7th bit. You can see first bit is connected to 7th. Second one, the second bit over here, input, is connected to first. So what can be the permutation table? Can you tell me quickly? What can be the permutation table at this point? Can you quickly tell me? I'll just try to remove this. My question is, you have a permutation table over here. What will be the permutation table given these are the possible combinations? Can you give me quickly? Let's start with first output. First output is 2. So in the bracket you are writing 2. Second is correct 8. Third output 3. Fourth output 7. Fifth 6. 1. 7. 4. 8. 5. That's the permutation table. That's why you did the question beforehand. Understood? So that is happening. That permutation table is existing in that black box. And the combination is in that way, after which this is completely randomized. And that random data is coming over here and we are calling that as a middle text. We are not bothered with the middle text, but the middle text is somewhere is the scrambled output. That is the input to the next round. You can see round 2 over here. So that middle text is coming to the next phase. Now round 2 is just the same repetition of the previous round. They all will be same. So the same process goes on. But except that the key is here K2. So K1, K2. Now if you imagine a 16 round of this, so K1, K2, K3 up to K16 will be generated. And each and every round will have a different set of keys. And each and every round will have its input from the previous output. And the previous output will have the combination of permutation of different S boxes. Can you visualize the scenario how the randomized thing is happening? So let us quickly wind up at this note. So this is the same thing they are discussing over here. So if you observe that the second round, bit 8, this is we are taking only one bit, 8th bit of the input, 1, 0, 1, 1, something is there. So the 8th bit is actually affecting 1, 3, 6, 7. You can see here. So cipher text, in the cipher text, the first, the third, the 6th and the 7th are getting affected by a single bit at the input. And in the same manner, each and every bit will affect individually. Now you just magnify the whole thing, expand this for 64 such bits. Understood? So how the process will get convoluted. Okay? So that's basically diffusion and confusion for a cipher text. Let us see if we can just start off with the Fiesta Cipher. I'll just start off with something and then we'll come back in next day and we'll finish it off. This whole process that you are looking at is still not very secure. Okay, so you can see the modern block ciphers, they are to be divided into certain rules. Remember when we discussed last class, like not the last to last class, I told you that you will soon find that a function will be used at some point. Do you remember the function? I told you function of certain key K1, X1, something like that. Don't know whether you remember it. Let me get back to that slide. This one. I told you that the function will be playing a very important role where the function will relate the X1 to output Y1. And there will be certain rules which will be imposed on it. This Fiesta Cipher is a process which is the backbone of DES where the same diffusion confusion element that I showed you right now will be applicable but with certain rules, with certain conditions. So we'll just see it and then I'll come back to next day and we'll finish it off. One minute, give me just 1 minute. So let me just show you that. So just observe over here. This is my plain text. This is also my plain text. So this is the first time it will happen that the plain text or the message will be divided into two halves, left and right. The left will be operated by certain functions, for example, over here. Okay. Although this P2 is this side, you don't, I'll show you the diagram itself. This is better. I think it will be less confusing for you. You can see left and right. And the left will be kept as it is, but right will be used by a function, certain function. That function will be again a factor of the key being used. K1, K2, K3 up to K16 for that matter. So not only that the key is getting XORed with the plain text, but there is certain rule on top of it that will make the combination itself randomized. Right, so that's basically the Fiesta Cipher diagram for that matter. Very simply you can observe that what we are doing, we have a mixture over here. The mixer, what is doing, L1 is a part of the plain text and R1 is getting combined through this function and the combination is called as L2 and R2. Okay, so that's where it stands. So you are improving the security even more. Okay, so that is where we end our discussion today. Let us not jump into Fiesta Cipher because it is a very important topic. So let us stop at this point. We have discussed up to the diffusion and confusion made in Block Cipher and how it's used. I'll upload the material of this. Please go through it, all the numericals and the type, because this will be useful to understand the next this class. So please go through it. All right. Thank you.